Howdy. I'm in the second section of our last chapter. I think it's chapter 11, sequences and series. Second section is packed with little ideas. If you could bother to read it, it'd be great, because I can go over these with you, but when you read the examples and you see what tools you have, it's kind of nice. So today it is convergent, divergent, and telescoping series with our guest star Coco Bananas, who's doing fine. And so am I. Hope you guys are well. So one of the ways you can inspect a series, which is a bunch of numbers being added together, one of the ways you can inspect it is by seeing what it actually does when you add a term. So they call it the sequence of partial sums. So the example that we did in the previous video, where we added from the 1 over the powers of 2, 1/2 plus 1/4 plus 1/8 plus 1/16. If you do the sequence of partial sums for that series, it's kind of pretty, because 1/2 plus 1/4 is 3/4. Throw on an eighth, get a common denominator. Honest to God, it's 7/8, which means that, if you're looking at this and playing with this for a second, I could ask you 1/2 plus 1/4 plus 1/8 all the way out to plus 1 over 164 or 1 over 256 or 1 over any power of 2, and the answer is going to be that denominator with 1 less in the numerator. And the evidence being that the sequence of partial sums seems to be getting closer to 1. It doesn't pass 1. It stays less than 1, but keeps getting closer to 1. So it's not a proof, but what it is you get a chance to inspect a sequence of numbers and say, is there a pattern here? Is this pattern leading somewhere that I can name? So they call this a convergence series when the infinite sum, like this one right here, when the infinite sum appears to be heading towards some small, or not small, but finite number. It's heading towards some number that you can get a grip on. So this guy here is I grabbed it out of the homework. Let's try this problem. The instructions were, do a sequence of partial sums, do a sequence of partial sums, do a sequence of partial sums, and if it looks like it could be convergent, then find the sum. So in other words, if you got a convergent series, apparently we can find the sum. This one's a famous kind called a telescoping series. We'll see what that means in about a minute and a half. So here's my little table. I didn't go very far. Here's my little table of sequence of partial sums for n equals 2, 3, 4, and 5. I did, well, when n equals 2, I have 1 over 2 times 4, so that's 1 over 8. When n equals 3, I have 1 over 3 times 5. 3 times 5, yeah, that's 1 over 15. But it gets added to the 1 over 8. So add the 1 over 8 plus the 1 over 15, I think it's 23 over 120. No common denominator, so I had to get one. And then I do the 4. So that's this guy plus 1 over 24, because that's 1 over 4 times 6. That one simplifies out to be 7 over 30. And I did the decimals, 1/8, 0.125, the 23 over 120, the 0.196 bar, 0.23 bar for this one. So you can see the sum is increasing, but the amount that it's increasing by seems to be decreasing. It went from, this went up 7/10. This one went up 4/10. This one went up 3/10. So it's increasing, which makes sense because you're adding stuff to it. But the stuff you're adding to it is getting less potent. You're adding smaller pieces. So it could easily be the case that it's convergent. So we're going to work as if it's convergent. And the first step is to say, well, I'd like to deal with this sum, because that's the thing inside the big summation symbol. I'd like to deal with this. And I recognize that it's partial fractions. So I broke it up, and I find that I get a 1/2 for A and a negative 1/2 for B. And we're going to pick up from there on a blank screen because we need some space. But that will give us the actual sum. All right, so here's the trick. Here's a useful trick. If you can rewrite this as a difference, a subtraction problem, you got a real chance of getting the actual answer. It is a rare thing. It is a very rare thing to get the actual sum for a infinite series when it's not pretty. It's not coming from a picture. So here we go. Let's take it from here. This is from the partial fractions that I had on the board. You could, go back and look at it if you want to see the steps of it. And anyway, so there's a 1/2 on each of these. So I factored out a 1/2 out front. You can do that when you have a constant times each term. You can factor it out. It's called the distributive law. So I factored out a 1/2. and I have this thing. And now this sum does the following. 1/2 times, okay, so when n equals 2, I get a 1/2 minus 1/4. When n equals 3, I get a 1/3 minus 1/5. When n equals 4, I get a 1/4 minus 1/6. When n equals 5, I get a 1/5 minus 1/7. When n equals 6, I get a 1/6 minus 1/8. Does anybody see what we can do? Anybody itching to cancel? Anybody? Hello? Hello? I'm itching to cancel. I think we can cancel some stuff here because there is a minus 1/4 and a plus 1/4. So that one goes. There's nobody taking on this 1/3 because if you remember, we did a 2 steps up kind of thing here for the subtraction piece. So we're never going to get a minus 1/3. This 1/3 lives. But do I get a plus 1/5 for that minus 1/5? I do. It's right there. Do I get a plus 1/6 for this minus 1/6? I do. It's over there. So what happens now is, if you notice, after this 1/3, everybody takes a turn canceling everybody else. You got your 2 steps off, so they don't cancel right away. But the subtractions for canceling are there. So what's this answer? What does this sum add up to? Let's call on Dom. Dom says, we'll take the 1/2, and you have this 1/2 plus the 1/3. 1/2 plus 1/3, that's going to be 3/6 plus 2/6, that's 5/6. This is 1/2 of 5/6, otherwise known as 5/12. So apparently that's what it adds up to. This sum adds up to 5/12, believe it or not. So what would convince you? Well, if you wanted to, you could, with your calculator, do this thing for as many steps as you wanted to, what I did with the sequence of partial sums, and see if they head toward 5/12. Well, let's see what 5/12 was. Remember, we left off with 0.262, and 5 divided by 12 is 0.416 bar on the 6. So this is, we weren't getting too close to it in our sequence of partial sums, but that's what this adds up to. But we only did 5 terms. You know, we could have done more. So that's how these things go. You get some evidence, and then you go on. Now, we will have better truths. Let me give you a sweet little clue here. Let me give you a sweet clue. This is like 1 over n squared. 1 over n squared, n equals 1 to infinity, is convergent. N squared, n cubed, n to the 4th, they all converge. However, there's one famous one that doesn't converge, and that's just plain 1 over n. And that's the one I'd like to show you, give you some evidence that this guy diverges, which is really funny. But let me give you some evidence about why it diverges. All right, now this is not a proof, but we could spend more time on it. There's some very famous proofs for this. Now this series has a name. It's called the harmonic series. Has a big place in math because it's sort of like the boundary line of convergent and divergent series. Stuff that's related to this guy diverges, and stuff that gets smaller faster than this guy, you know, something with an n squared down here, will converge. So let's see what our evidence is for this thing. So I can add up the first 3 terms. 1 plus a half plus a third. I'm bigger than 1. I'm bigger than 1 as soon as I do 1 term. But as soon as I go to 5 terms, I pass 2. I go to 11 terms, I pass 3. I go to 31 terms, I pass 4. I go to 83 terms, I pass 5. It's a fact. How big do you want to go? I will tell you, or another mathematician can tell you how many terms you have to do. So do you want this sum to get bigger than 1,000,000? Yeah, you'll have to add up a zillion terms, but it can be done. You can add up a finite number of terms and it will get bigger than 1,000,000. So this is divergent, very famous divergent series. Now that gives us further consequences. So for instance, what about if I have start with 1/10? 1/10 plus 1/11 plus 1/12 plus 1 over 13, etc. So all I do is it's the same as this series, but I knock off the first 9 terms. What do you say? Do you say divergent? It is divergent because this thing, the infinite sum is infinite. If I take off a finite number, Infinity's still left. These terms still don't get small fast enough. They don't get small fast enough to converge. So that's what's going on with divergent series. You can have a sequence of partial sums that, you can see the sequence of partial sums doesn't seem to be zooming in on a number. They just keep getting bigger. The sequence of partial sums just keeps increasing. Well, it's evidence you got a divergent series. But the main thing is just look at what your power on n is, and that'll take care of it. So try some problems from section 2 of the last chapter of this semester.